so this recording is for marine biology, and it's module 1. And we're going to try to get through all of module 1 as part of this recording. So marine biology, module 1. And this first module is going to cover the oceans of Earth. So let me give you a few bits of information about the oceans. I mean, you've probably heard the figure that about 75% of the Earth is covered with water. It's actually closer to 72% of Earth is covered by water. So obviously we're talking about a large portion of Earth that is covered in water. So let me show you a figure that will show you that shows us the major bodies of water associated with Okay, so this figure shows the Earth with its basins, and the first things I want to point out to you are that if you look at the northern hemisphere versus the southern hemisphere, so northern hemisphere here, two-thirds of the land mass of Earth is in the northern hemisphere. So you can, if you look at the northern part of this figure, you can tell that there's more land and less water. So two-thirds of the land mass of Earth is in the northern hemisphere. And yet if we look at the southern hemisphere, 80% of the southern hemisphere is water. So much less land and more water in the southern hemisphere compared to the northern hemisphere. So then let's look at some of these tables and figures. So this table 1.1 shows us the 4 oceans, and these are listed based on their depth and their size. And so you can see that the Pacific Ocean is the largest. It's the deepest ocean, but also the largest ocean by its area. And then the Atlantic Ocean is next. Again, here's the depth, and here is its area. And then the Arctic, then the Indian Ocean, and then the Arctic Ocean is the smallest, and it's also the most shallow. So most shallow and also the smallest is the Arctic Ocean. Okay, and then in addition to these oceans, we have in addition to those oceans, then there are other bodies of water like the Caribbean, the Arabian Sea, the Mediterranean Sea, and then one that maybe some of you have been to is the Gulf of Mexico on the southern border of the United States. So these bodies of water actually serve as connections between the oceans, and what that allows for then is that it means that organisms are able to move they're able to move from one ocean to another because of these bodies of water that connect the oceans. If we look at Earth's, if we look at Earth and we think, actually, let me go back to this figure that we were looking at before. So let's look at this figure, and I'm not going to spend a lot of time on this except to point out that, the outer portion of Earth is called the crust, and then inside that is the mantle, and then we have the outer core and the inner core. So I specifically want to look at and say a few things about Earth's crust. Earth has different types of crusts depending on whether that crust is covering the ocean or whether it is covering covering land. So if the crust is covering the ocean, then we call it the oceanic crust. And so that's the part of the crust that covers the oceans. And this crust is about 3 miles thick. And it is comprised mostly of basalt, which is solid lava. So lava that has lava from an earthquake that has hardened. Okay, then the part of the crust that covers land is referred to as the continental crust. So the continental crust covers land, and it is thicker. It's about between 12 and 30 miles thick, and it is comprised primarily of granite. Okay, so different substances cover or make up Earth's crust depending on whether that crust is over the oceans or whether that crust covers land. Okay, now I want to talk about something that is called, most of you have probably heard of this before, but it's called Pangea. This is pronounced Pangea. And what Pangea is a large supercontinent. And it is believed that Earth's land masses once existed as a large supercontinent called Pangea, and then because of how the plates shift and interact with each other, this led to continents drifting away from each other. So that now what Earth looks like are these larger plates that are on Earth's mantle. So let's take a look at a figure of that. Okay, so this figure is showing the major plates of Earth's crust. So it's thought that once these plates, these land masses were together, and then due to radioactive decay in Earth's mantle, and then heat that's being released because of that, then there was movement in these plates that then resulted in the continent land masses as we know them to exist now. Where these plates come together, so anywhere in where these dark lines are drawn are where the plates in Earth's mantle come together. And where these plates come together, you essentially have one of two things that can occur where those plates meet up with each other. And one thing that can happen where those plates join up with each other is that you can have mid-ocean ridges. So you can have these ridges that are present in the oceans. And so basically what you get there is you get a chain of underwater volcanoes. So again, this is where those plates come together. Okay, and then the other thing that we get where these two plates that come together are the opposite. So here you get ridges, and the opposite of that is that you get deep depressions that are called trenches. And if we were to look in the areas around these ocean ridges, this actually tends to be where earthquakes can occur. And then in the area around the deep depressions is where you can actually get volcano eruptions. Okay, so again, this is where the plates, where the large plates that are part of Earth's mantle, where those plates join with each other or butt up with each other, you'll either get mid-ocean ridges or you'll get deep ocean depressions. Now, this plate movement, when we talked about about those plates once being a supercontinent and those plates having drifted apart, this plate movement occurs very slowly. So it actually occurs at a rate of about 2 to 18 centimeters per year. So we're not getting huge amounts of movement, but over time, the plates are moving apart from each other. So then you might ask yourself, well, if these plates are moving, however slowly, if the plates are moving away from each other, then why isn't Earth's surface increasing? Why isn't the surface of the Earth getting bigger? And the reason for that is when two plates are moving toward each other and they collide with each other, what often happens is that one plate will move below the other one. And when that happens, that's called a subduction. So this is when plates move toward each other. And collide. And one plate goes below the other. And that explains why Earth's surface is not actually increasing as those plates are moving around. Okay, so that is subduction. So now we are ready to look at the ocean bottom. And I'll put up a figure of that in just a moment, but let me first just list the 4 areas that make up the ocean bottom, and then we'll look at them in a figure. Okay, the first layer, the first area is called the continental shelf. And the continental shelf makes up only 8% of the ocean. And yet, this is where most of life in the ocean exists. So most of the living organisms are going to be um, present in the continental shelf. The continental shelf, it's at the edge of the continent. It's shallow, and it's also gently sloped. And because it's shallow, that means that more light can penetrate it. There's more light available on the continental shelf, in the water of the continental shelf. And that also, and if you remember back to your biology, then that also means that there are more producers. So photosynthesis can take place, so you'll have more plants and things like algae that rely on light in this area, in the area known as the continental shelf. Okay, so that's the first area of ocean's bottom, is the continental shelf. Okay, then the next area is the continental slope. And you'll see when we look at the figure in just a bit that the continental slope is steeper. So it's a big drop off. Okay, so that's the second area. The third area is called the continental rise. And it's called the continental rise because, and you'll see this from the figure in just a moment, that because at the continental rise, we get a buildup of sediment so that you actually get a somewhat of a rise in the ocean bottom. Okay, then lastly, the last area is called the abyssal, not abysmal, but abyssal plain. And the abyssal plain is that area that is greater than 10,000 feet below the surface. And the abyssal plain is flat. And however, the abyssal plain is not the deepest part of the ocean, because the trenches that we talked about previously are deeper. So the trenches are actually, they're actually can be like between 6 and 7 miles deep. So that's much deeper than 10,000 feet. So the trenches are the deepest part of the ocean and not the abyssal plain. Okay, so let's erase this and then we'll get that figure up so that we can see the different parts of the ocean bottom. Okay, that's not the figure I had meant to put up, but this we talked about subduction and how when plates collide, one plate can slide over the other, and that can, that's what keeps Earth from getting bigger and bigger. Okay, so this figure then shows the different areas. So the first area is this continental shelf. Remember we said it's at the edge of the continent. So here's land over here. It's the edge of the continent. It's very shallow. And there you can get kind of a gentle slope to it. Then you have the continental slope, which is a much deeper slope that occurs here. And then the continental rise, where you get this buildup of sediment, and you can actually get a slight rise in the in the ocean's bottom. And then you have the abyssal plain, which is anything deeper than 10,000 feet, and you can see that it's flat. Okay, so let's get back to our whiteboard, and now we're going to turn our attention to talking about water and the properties of water, because that's important as we talk about what ocean water is like. So those of you who have had chemistry remember that a water molecule is made up of an oxygen and then two hydrogen atoms. Okay, so 2 hydrogens and 1 oxygen, that's water. And the oxygen and the hydrogens share electrons. So again, those of you who have had chemistry, if you haven't, that's okay. Those of you who have had chemistry, remember that when you have a chemical bond in which electrons are shared, that's called a covalent bond. And when a covalent bond exists, often one or more of these molecules pull on the electrons harder. And so they get their share of those electrons longer or more often than the ones that have than the atoms that do not pull on those electrons. So remember, the electrons are negatively charged. So they're negative. And in a water molecule, the oxygen atom has a stronger pull. So oxygen pulls on the electrons with greater force than the hydrogens. And basically what that means then, since the electrons are negatively charged, it means that there is a slight negative charge on the oxygen atom, and there's a slight positive charge on the hydrogen atoms. Okay, so remember that the oxygen within a water molecule has a slight negative charge on it, and the hydrogens have a slight positive charge. Okay, let's erase this. Oop. So when if we have water molecules that exist, so let's say, so we have an oxygen here and hydrogens here. So this is an oxygen, these are hydrogens. I'm kind of crooked, but okay, and I have another oxygen here and 2 hydrogens here, another water molecule. oxygen, hydrogens over here. Oxygens, and we have two hydrogens over here. So, and again, remember that there's a slight negative charge on the oxygens. So wherever there's an oxygen, I'm going to put a negative charge, and there's a slight positive charge on the hydrogens. Okay, so remember, and you know that positive and negative charges attract each other. So in water, the positive charges on the hydrogens will be attracted to the negative charges on the oxygen. So water molecules will bond with each other because the positive charges on the hydrogen of one water molecule will be attracted to the negative charges on the oxygen atom on the others. And that is called hydrogen bonding. So hydrogen bonding is the way that different water molecules are attracted to each other and bond with each other. And because of hydrogen bonding, water has what is called surface tension. And what that means is that on the surface of water, the water molecules will tend to stay attracted to each other. They'll tend to stay close to each other because of these attractions between the hydrogens and the oxygens. And so this explains things like why those insects that are called water striders, why they are able to land and stay on the surface of the water without breaking the surface, because of these bonds, these hydrogen bonds that exist between one water molecule and another. And maybe you've tried the trick where you can try to get a needle to float on the surface of the water. And if you do it really carefully, you can do that. And it is because of surface tension and because of the hydrogen bonding properties of water that things like water striders or even needles can stay on the surface of water and won't break the surface of the water because of the surface tension that exists in water. There are some slight differences between seawater. We'll talk some more. We'll deal with this in more detail in just a moment. But if we look at seawater and freshwater, so because of as liquid water cools in seawater, the molecules move less. So as this cools, the water molecules move less. And so they stay tightly packed together. So that they take up less space. So because of that, cold seawater sinks below warm seawater. So if we look at a at a body of salt water like an ocean, the colder seawater will be lower, and the warmer seawater would be at the surface. Now that is true of freshwater also. So freshwater also sinks. It becomes more dense and sinks as it gets colder. However, for freshwater, this is true only up to, or only down to 39 degrees Fahrenheit. So below 39 degrees Fahrenheit, if it's fresh water, so below 39 degrees, fresh water becomes, let me erase that. Fresh water becomes less dense as it gets colder. So what does that mean? Well, if fresh water becomes less dense as it cools, then that means that in fresh water, ice floats. And you've all seen that. So if you take a glass of water and throw in some ice cubes to that glass of water, if you throw in some ice cubes that are, if they're frozen, they're below 32 degrees. So when fresh water is below 39 degrees, it becomes less dense, and you will see that the ice will float on the surface. So why is that important? Well, it's important because what that means is that so first of all, it's very unusual for something in the solid phase to be less dense. Water is one of the few substances that is less dense. So water is less dense in its solid form. So that means it floats. And the reason that is important is that it's important for aquatic organisms because since ice floats, it insulates and it keeps the water below the ice. So the ice will stay on top, and it provides a layer of insulation so that below that water, the water doesn't cool down too much, so that then lakes don't freeze, rivers, shallow rivers don't freeze, so that they don't freeze into a solid mass, so that life can still be maintained there throughout the year. So I used to live in Minnesota, and ice on some of the lakes in Minnesota can get to be a couple of feet deep on the surface, but in a deep lake, that layer of ice will serve as an insulator so that the water below it doesn't freeze, and aquatic life can live then throughout the winter because the lake will not freeze all the way down. So that's an important quality of water, is that at below 39 degrees, water actually becomes less dense as it gets colder rather than becoming more dense. Another quality of water that we need to talk about is something called the specific heat. And specific heat is the amount of energy needed to raise the temperature of 1 gram of water, 1 degree centigrade. 1 gram of water, 1 degree C. So the specific heat for water is equal to 1.00 kilocalories for each 1 degree C. So in other words, it takes 1 kilocalorie of energy to raise the temperature of a gram of water 1 degree C. And for water, this is a high specific heat. Compared to other substances. So in other words, it takes a lot of energy, it takes more energy to raise the temperature of water compared to other substances. And that also means that the opposite is also true. So if it takes a lot of energy to raise the temperature of water, it also means that you have to remove a large amount of energy or a large amount of heat in order to cool it down. So why is that important? That is important because since it takes a lot of energy to either heat up or cool down water, that means that water maintains a much more stable temperature than some other substances would. So the temperature of water doesn't change very quickly, so that the water environment stays pretty constant. And that is, again, important for maintaining life of organisms that live in the water. Okay, another quality of water that we need to talk about is that water is a solvent. In fact, we call water the universal solvent. And a solvent is something that can dissolve something else. So water is able to dissolve a lot of substances. So that's why we call it the universal solvent. So one of the most prevalent things that is dissolved in water is sodium chloride. So this is sodium and chlorine. So sodium chloride, which is just salt. So water is, there is salt dissolved in the oceans of the world. So sodium chloride is one thing that is dissolved in the ocean, or dissolved in the world's oceans. But there are also other things, and generally we think of, when we think of things getting dissolved in water, they're going to come from one or two places. They're either going to come from solids. Let me make that a little bit. So they'll come from the rocks on land, and then will get dissolved in the water. Actually, the solids, the rocks on the land, that would go into the rivers, and then from the rivers it would eventually make its way into the oceans. Okay, so the solids that are, often these are positive ions. So they're things like magnesium, potassium, sodium. Okay, so those are things that the solids that get dissolved in water. And then secondly, things get dissolved in water from Earth's mantle. And that primarily happens through hydrothermal vents. I'll show you a figure here in just a moment. So you get liquid lava that escapes through the mantle by these hydrothermal vents, and usually these are negative ions like chlorine and sulfur. So this is sulfur and chlorine. Okay, so the positive ions usually come from rocks on land and lead to positive ions, and then from the Earth's mantle we get the negative ions like chlorine and sulfur. And I'll erase this and then I'll show you a figure, a couple of figures that show that. Okay, so this is showing how we get so you have a volcanic eruption, and you have that molten lava, and some of it will escape will get into water from underneath through these hydrothermal vents, and then, as we said, the other solids will come from the surface of the earth. Solid things get washed into the rivers, and then those rivers empty into the ocean. Okay, the next quality that we want to talk about with regard to the ocean water is its salinity. And salinity refers to how much salt is dissolved. And for the ocean, we express that as the grams of salt per 1,000 grams of water. So how many grams of salt is in 1,000 grams of water? And so we just abbreviate that or talk about it as parts per 1,000. How many parts of salt are there per 1,000 parts of water? And so if something has 32 grams of salt, we would say it has 32 parts per 1,000. And if you think about that percent, so percent means 100, right? So when we say, so then parts per 1,000 is actually listed as like this. So this is parts per 100 or percent, and parts per 1,000 is like that. So 32 parts per 1,000 would be signified as that. So this means there's 32 grams of salt for every 1,000 grams of water. And the salinity of the oceans stays pretty constant. The one place that the salinity changes is near the mouth of rivers. But so near where the oceans are, where the rivers are dumping into the oceans, the salinity changes, but otherwise the salinity stays pretty constant. Let me show you a figure that will just allow us to look at some of the actually, I don't know if I have this. Let's see. Yeah, okay. So there are different ions found. There is a table in your book, and that gives you the salinity for different ions. And as I said, they stay pretty constant, except when you get near the mouth of rivers. Let me go back to the whiteboard before we talk about this figure. How do salinity temperature and density, how do those all relate to each other when we talk about the ocean? So as water gets saltier, as you might imagine, as it becomes saltier, it becomes more dense. And we've already said that colder water, to a certain point, colder also becomes more dense. Until it reaches the point where it freezes. So what that means is that the saltier and colder water would be deeper, and the warmer water and the less saltier water would be more shallow. So the saltier the water and the colder the water, the deeper it would be within the ocean. Okay, let's talk about why the ocean is blue. And to do that, I want to look at a figure. Okay, so this figure shows the light penetration, how light penetrates seawater. So if you remember the colors on the spectrum, the visible light spectrum, you memorized Roy G. Biv, so red, orange, yellow, green, blue, indigo should be in here, and then violet. And the main thing I want you to see from this is that the blue light, the wavelength of light that is blue, penetrates water to a greater depth than any of the other wavelengths of light that make up the visible light spectrum. So because the blue wavelength of light penetrates water more easily into a greater depth, then the ocean looks blue. So it's just due to the penetration of the blue wavelength of light. Okay, how about pressure? How does pressure affect the ocean? So as you know, the atmosphere, so all the molecules that make up the atmosphere do press down on Earth with a certain amount of pressure, and we refer to that as the atmospheric pressure. And so on land, the atmospheric pressure is 1 atmosphere, 1 ATM, or 1 atmosphere. Well, as you might imagine, water is heavier than air. So when you look at the pressure that water exerts, you're going to add 1 atmosphere for every 33 feet. So in other words, if you're on land, the pressure that you experience is going to be 1 atmosphere. If you're 33 feet below the surface of the Earth, then it's going to be 2 atmospheres. If you're 66 feet, then it's going to be 3 atmospheres. So the pressure that is experienced as you go to greater depths generally happens at a rate of about 1 atmosphere per 33 feet. And you've all experienced that, where if you dive down even 12 to 15 feet, you feel that increased pressure in your ears. The pain that pressure causes as your eustachian tubes try to somehow equalize that pressure. So if you've ever dove down to a depth, then you've experienced that change in the pressure as a result of water. Now, what does this mean with regard to life in the ocean? Well, generally it means that most organisms can only survive in about 1 to 3 atmospheres. So that means that most of the life that is present in the ocean is going to be present within the first 100 feet of the ocean, because below that, most organisms are not going to be able to withstand the high pressures associated with that. Okay, the last thing that we need to talk about with regard to the ocean is the motion of the ocean. So those who have been to the ocean know that there's a lot of motion that takes place within the ocean. And one thing that we see pretty easily when you go to the ocean are the surface currents. So you can see the motion of the ocean, the waves. This is horizontal movement of the water. And this is due basically just to wind. So as the wind is blowing across the surface of the ocean, it sets up that horizontal movement of the ocean. Okay, then the other main way that the ocean moves is with is what we call the tides. And the tides are due to the gravitational pull of the moon and the sun. And because the moon is closer to the earth, it has the greatest effect on the tides. Even though the sun has a much greater mass, because it's farther away, it doesn't affect the tides as much as the moon. So most of the gravitational pull of the moon and the sun on Earth, most of the effect is going to be due to the moon, just because it's closer to Earth than the sun, even though the sun is much more massive than the moon. So let me show you a figure. Okay, so this figure shows the gravitational pull on Earth that is due to the moon. And basically what I want you to see is that as the moon pulls on the ocean, so here's the moon, it's going to pull on the ocean, and it causes the ocean to bulge toward the moon. Okay, so you can see this bulge here due to the moon. So this part bulges toward the moon, and then on the other side, it actually bulges away from the moon. So as Earth spins on its axis, that means that any point on Earth will go through the non-bulge phase and the bulge phase twice a day. So here we see this figure is showing a house, and as you go through the 24-hour day, there will be, so here the house is in the non-bulge phase, so that would be considered low tide. So this is low tide. And then when this structure is in the bulge phase, that's a high tide. And then as the day continues, it goes, and now it's in the non-bulge phase, so that would be low tide, and now it's back into the bulge phase, and that would be high tide. So there are two low tides per day and 2 high tides per day. As at any point on Earth, as Earth spins on its axis, and as I said, this is mostly due to the sun. Mostly due to the moon. The sun doesn't have as much of an effect because it's farther away. Okay, one other thing that we'll talk about and then we'll be done. Okay, so that was basically talking more about the horizontal motion of the ocean, but we also can get the movement of water in the ocean in a vertical direction. And so then we pretty much divide the ocean into 3 layers. We have the surface layer, which is from the surface down to about 300 to 600 feet. And as we've already said, that this would mainly be warmer water and less dense water. Then the next layer is called the thermocline. And this would be from about 600 feet to 1,500 feet. So this water would be colder than the surface layer and also more dense. And then we have the deep layer. And the deep layer would be anything below 1,500 feet. Below 1,500 feet below the surface. So this, again, would be even colder and more dense. Usually these layers stay where they are and you don't get a lot of mixing, but if the density of one of these layers were to change, then, so if this becomes, for some reason becomes more dense, then the surface layer can actually move down below the thermocline layer. And you can get a mixing of these layers or even a partial reversal of these layers. And that's not actually a bad thing because if the surface layer comes down and into the thermocline layer, it will actually bring with it some oxygen because there's going to be more oxygen on the surface, and then the deeper layer will move up to the surface, and it can carry nutrients with it. So one time when you might get a reversal of these, let's say that you get some evaporation of water. So if some of the water in the surface layer evaporates, then that means this layer is going to become more dense. And so the surface layer may move down below the thermocline layer. And as it does that, it will carry oxygen with it. So you'll get more oxygen down to the organisms that are living farther down below the surface. And then when the thermocline layer goes up to the top, it will carry nutrients, and that can benefit things that are living on the surface. So the vertical layers are the vertical layers of the ocean are the surface layer, the thermocline layer, and the deep layer. You don't often get a mixing of those, but you can. So that is all the material we're going to cover in Module 1. So let me go ahead and show you a figure of those layers. We'll just look at this quick and then we'll be done. Okay, so here's the surface layer. And then the intermediate layer here is called the thermocline layer, and then the deep layer. It's going to get colder and more dense as you go down, and sometimes you can get a mixing of these layers, although that doesn't usually happen. Okay, so that's it for Module 1 in Marine Biology.